we discussed about the abstract states and also events for our initial model of the FTP. Let's now try to prove about the validity of our initial model. Namely, we're going to focus on the invariance, both establishment and also preservation. And for the deadlock freedom, I'm going to leave that to you as an exercise. In this case, it's rather trivial to do so, but still do the exercise about proving the deadlock freedom. It'll be good for your learning. Right, let's talk about invariant establishment. The number one question: how many sequence do we need to prove? Well, how many do we need to formulate in the first place? And always remember, invariant establishment is not really for every event. It's only for the special events in it. When you actually first launch the system, you want to make sure whenever you first launch the system, all the invariant conditions will be established. So that's why the number of sequence only depends on the number of invariants. It doesn't really depend on how many events you have in your model, because you always have the single init events. So that's why that factor there is not really here for the multiplication, right? So only about the number of invariants. How many invariants do we have? If you look up, we got 4. So that means we're going to generate 4 sequence in total in order to prove about the establishment of the invariance for our FTP initial model. Right, so I actually got the answer on the slides already. However, I think it might be worth doing some of them together just to brush up your memory about how to formulate a sequence, which will be important later for the assessment as well. Let's talk about it. Right, for invariant preservation, invariant establishment, let's recall what it should be, how it should be formulated. This will be the proof obligation rule. You can see in the hypothesis, we only need to include the axioms. So that means we don't have to worry about invariance, because there is no pre-states for the init events, meaning that we cannot really assume the invariants are already maintained or already satisfied in the pre-state. So that's why we have to disregard the invariants. Only include the axiom, and then this part over here, I of j, we're going to index every invariant. How many invariant conditions do we have in the post states? We got 1 here, 2, 3, and 4. So that's why I just want to do 2 exercises with you together. We talk about init events. It is going to establish the invariants, and we're going to talk about each condition one by one. The first one we want to talk about is 1a over here. And the second one is 2, which is over here. For the rest of the 2 proof obligations related to invariant establishment, it will be your exercise, right? Let's now do it together. And of course, don't forget, this part over here is about effects based on the before-after predicates of the init events. That's something you have to remember as well. The same principle will apply when we formulate the sequence for invariant preservation. Let's now do it. So the first one here, let me highlight it maybe in pink. Invariance 1a. So this is the one to formulate. And what will be in the antecedents? Let me just put green for antecedents. Antecedent is going to be all the axioms, in which case we got all the axioms exactly over here, right? So we have to repeat them. No way around. Let's do it. So we got n larger than 0, f, the file on the sender side, is a member of the set of all total function between 1 to n, and then d, right? Total function. And also the Boolean data type. You cannot assume the Boolean type is actually there. So that's why we have to define that explicitly. True. And as a side note, the Boolean type is more like a programming concept. So that's why you have to define that explicitly if you want to include it in your mathematical model. False. Right, we can definitely copy this in a moment. And these are all we have to include in the hypothesis, just the axiom. So that'll be the hypothesis. Okay, let me put a turnstile over here. What about the goal? The goal will be the post-state evaluation for this invariant here should be satisfied. Let me put a post-state version first. So that means G prime over here is a member of, and I noticed some embarrassing typo over here. I think this one here should just be G is a member of. I'll fix that in your notes. Okay, let me just cross it out over here. So this should be, so this one should not be there. Oh, sorry. So this part over here should not be there. Let me just get rid of it. And that one there should be 1 dot dot n, and then partial function d. And one thing to note, we don't really put n prime and we really don't put d prime, simply because n is actually a constant which never changes. So there's really no point to really compare its pre-state and post-state. They always remain the same. And also for the d over here is also a carrier set. Carrier set is also part of the static part of the model, so that's why it also doesn't change. So the only variables we have to get a prime is those variables that's under the variable section, the dynamic part over here. Right? So this would not be exactly correct because we cannot really have the prime variable in the sequence. So we have to simplify this. But how do we do that? Right? So this g prime over here, we can simplify it by referring to the before-after predicates for the init events. You can see this is the before-after. Well, this is only the action, right? So you kind of remember how we figure out the before-after predicate, right? So it's going to be g prime should be equal to empty set, and also b prime is equal to false, right? So that's the before-after predicate. Don't forget. Right, everything has been said earlier, and we have done many exercises previously as well. So we're going to replace the g prime here just by the empty set. So finally, the goal would just be, let me highlight it here, it would just be empty set is a member of the set of partial functions between 1 to n, the interval, and the carrier set d. And also we got a hypothesis, right? So that's the first proof obligation. What about the second one? For the second one here, we're just going to copy this part over here. For the hypothesis, it's going to be the same. Let me put it here. That part is the same. What about the goal? Let's try to do the similar exercise again. Let's see which invariants we want to focus on. Let me use orange. We want to do invariance 02, which is over here. Right, let me put it down, and we need to put a prime for all the dynamic variables. Let's now do it. So b is a variable, so b prime equals false. Implies g prime equals empty set. Right? You can see over here, only b and g are the variables. That's why I put a prime after them. And we have to simplify this by applying the before-after predicates. And we have already got it. So b prime should be replaced by, let's see. So the b prime over here should be replaced by false. And also the g prime here should be replaced by, okay, let me just make it a little bit smaller so I don't really cover the equal sign. So g prime here should be empty set. So what you end up having will be false equals false. False equals false implies empty set equals empty set. And it seems quite obvious to prove, right? But anyway, I'll leave that to a little bit later. Right, so that's a very quick review about how you can formulate the invariant establishment proof obligation. It's been a while since we have done this particular proof obligation, so I think it's worth reviewing. Right, and your exercise will be to come up with the formulation for the other two proof sequence related to invariant establishment. That would be your exercise. Right, let's now move back. And you definitely will get a solution on the slides, but I would suggest only look at them once you complete the exercises. Let's now move on to proving some sequence related to invariant establishment. The two we just formulated were this one here and also this one over here. We're also going to do their proofs together with you. And for the other two, once you formulate them, you can definitely compare your answer first, and then it would be also your exercises to really discharge them using a similar reasoning pattern, which we're going to show to you for these two. And typically, not always, but typically, for invariant establishment, the initial values, for example, empty set that the variables become, would be quite easy or straightforward to show that they actually satisfy the desired property we want to establish without using any of the hypotheses. It's very typical. It's very often the case, but not always. So you can keep that in mind. What about this one over here? It seems to be the case. We want to prove that the empty set, which is the initial value for this one over here, right? We talk about invariant 1A over here. So the initial value for G, which is empty set, is a member of the set of partial functions between 1 and n, and also D. And this one here is actually rather straightforward to really justify based on what we learned from lecture number 1 in weeks number 1 and 2, right? So what I would say is we have to do the following. We can simply say arithmetic over here, and then after that we can simply have, of course, if you want to use the monotonicity to drop all the hypotheses, you can do so as well. But for now, I'm just going to copy that since I don't want to apply that. N larger than 0, f a member of this total function D, and also Boolean. Of course, it might be more convenient if you simply use a monotonicity first to drop all of them, but I'll leave the choice to you. So it's going to be true and also false. Okay, just enough space. And then turnstile over here, I can simply say it is true. Oh, sorry, that should be here. And notice one thing here. This is more like a predicate true. On the other hand, the true and false over here are specific to the Boolean type we have over here. So over here, you cannot just put true, because it's a category error. You cannot really just put true, right? Let me just emphasize that over here. If you actually put, for example, just true over here, that is not correct, strictly speaking, right? Again, the true or top over here as opposed to bottom over here. So these are related to the predicates. On the other hand, the true and false over here are related to the specific carrier set that we actually define in the static part of the model. And after we have got this, are we now having a provable sequence? Indeed, because now we can see the goal that we want to prove is actually true. In that case, we can definitely apply one of the Axiom inference rule. Which one is that? You can look it up. So it's actually very trivial. It will be true that appear on the right hand side of the turnstile, and we are now proved. And for this arithmetic that we try to prove over here, I would say in the assessment you want to be very careful whenever you put the arithmetic inference rule, because you're claiming that to really go from here to over here is obvious. However, whatever you judge is obvious may not be so obvious to the grader, right? Or it may not be so true. So to be safe, I would suggest whenever possible, you should really put down some extra informal description about why you think arithmetic rule can be applied in this step over here. And what about in this case here? An empty set apparently should be a member of the set of partial functions between this left set and this right set. And how do we justify that? Let's now put it down. My take would be, we can say empty set is always a partial function whose domain and range are empty sets as well, right? So I think this one really explains in general the empty set will just be a partial function despite what the left and the right are. So this will clearly justify how you can go from here into true in the next step, right? Let's now talk about the next one, and let's prove this one here, which we also formulated earlier. And this one seems to be also quite straightforward to be proved directly without using any of the hypotheses. You can look a little bit more closely to convince yourself why. But for now, I'm just going to apply monotonicity just to show you the alternative, because we don't necessarily want to copy those hypotheses when we know they are not so relevant. By monotonicity, we can drop all the hypotheses. So that means we got turnstile over here, got empty hypothesis only. And then let me copy the goal again. False equals false implies empty equals empty. Seems to be very straightforward to prove, but let's now do it formally. Due process is important. Okay, over here. And we can easily simplify this part over here to be true, but we need to further justify that informally as well. But I'll do that in a moment. Let me just say it by arithmetic over here. We know that we can simplify the sequence over here, the go, into true. Right? Again, you should really know why. You have to put the predicate symbol true, the top, as opposed to just the true, which is a category error because true belongs to the Boolean carrier set, right? They are different. And let's now see how we can go further. Apparently, once you get the true being the go, we can apply, again, the same inference rule as before, right? So we can say the true actually appear to the right of the turnstile. So that's proved. And let's now try to further justify this arithmetic. Why could we actually go from this predicate over here into true? The reason is false equals false apparently is actually true. Right? Well, actually true. Let me say it again. False equals false is actually true. And then true empty set equals empty set is also true. So true implies true is going to give you true, right? Let's now write it down. So number one, we know that false equals false is equivalent to true because any expression is equal to itself. It's something called reflexivity, right? That's something you may have heard back in 1090. And number two, we got empty set equals empty set. It should be also equivalent to true. And number three, we know that by the truth table for implication, true implies true is equivalent to true. That's how we justify it. Right? So these are the three extra informal justification that we need to put down to really convince others that the arithmetic can really be applied over here. Alrighty. And that's about the two proofs I would like to go over with you. We still got these two sequences outstanding to be proved. And that will be your exercises. Alright, let's now move on to formulating and proving invariant preservation.